Hello everyone, welcome to the week 12 problem solving session for deep learning. So this will be the last problem solving session from my end. So today we will be talking about problems on VAE, variational autoencoder, and GAN networks. So let us get started. First we will discuss about VAEs, then we will move on to GAN. So the first problem that we have here is, during training a variational autoencoder or VAE, it is assumed that probability of z given x, which is the conditional probability of the latent code z given the input data x, is a normal distribution with 0 mean and identity covariance. That is, given an input sample which is x, the encoder is forced to map its latent code which is z to a normal distribution. Now, after the training is over, we want to use the VAE as a generative model. Then what should be the best choice of distribution from which we should sample a latent vector to generate a novel example? The options are normal with 0 mean identity covariance, 1 mean identity covariance, -1 mean identity covariance, and a uniform distribution between -1 to 1. So now our VAE training has been done. We want to use it as a generative model and we want to generate a sample like our data set. So what should be the distribution from which we should sample our latent vector and pass it through the VAE decoder so that we get a sample? So what should be that distribution? That's the question. So any answer from anyone? Any answer, guys? Like what should be the distribution of the latent variable from which you should sample to generate a new data point x? Okay, I'll explain the thing. So Jyoti is saying option 1, which is correct option, correct answer. Jyoti. Option 1 is the correct answer. So here in VAE, the idea is when you are training the VAE, you want to have your latent distribution, latent code distribution as a normal distribution with 0 mean and identity covariance, right? That way you trained the encoder. So your that way you trained your VAE, both encoder decoder. So your encoder is forced to map its latent vector to this distribution only. So the decoder, while training, it always so when the decoder is completely trained, it sees distribution from this distribution itself, sees samples, latent codes from this distribution itself, because it's trained that way. So now if you choose any other distribution or normal distribution with any other mean, then the decoder part of the VAE has not seen that distribution of the latent vector during training. So it won't be able to generate a meaningful reconstruction from such a distribution which it has not seen before. So whatever during training, whatever distribution you mapped your latent code to, that is the distribution that you should use while sampling your data point during using the decoder as a generative model. That should be the distribution used, because your decoder has already seen that distribution only. and it has learned how to map your data from that latent code which follows the normal distribution. So, you should sample from there itself. So, option 1 is the correct answer for this. Okay. Now, next one. Here we have given some graphical models. We have to say which one fully represents the VAE realization. So, which one of these 4 do you think is the correct realization of a VAE? Anyone? Option A. Yeah, everyone is saying option 1, which is the correct thing. So, what happens in VAE? So, there are 2 parts in VAE as we have learned during the lectures. So, we have the input X, which we pass through a encoder network, which gives us the latent vector Z, but this is not a deterministic one, it is a probabilistic latent vector, like it has a probability distribution attached with this vector. Then we pass it through a decoder and we get some reconstructed example, let us say XAT. So, this encoder portion basically models the QZ given X. So, given Z, it tries to map to the latent vector. So, that distribution mapping it does, and this basically does X given Z. So, given the latent vector, it tries to map to the distribution of X. So, here that is the case. So, X is basically our input data, this is our input data and this is our latent code. So, by using QZ given X, we go from X to Z, and by using Px given Z, we come back from Z to X. So, both ways are there. So, this is the ideal realization of a VAE using a graphical model. Now, next one. Why is the reparameterization trick used in VAE? The options are without reparameterization, the mean vector of latent code of VAE encoder will tend towards 0. Sampling from a VAE encoder latent space is non-differentiable, and thus we cannot back propagate gradient during optimization using gradient descent. We need to reparameterize normal distribution over latent space to Bernoulli distribution, none of the above. So, which one do you think is the reason of doing reparameterization? Yes, of course, option 2 is the correct one. So, if we use the latent vector itself as a if we sample directly in the latent space within the computational graph, then that randomness will actually break the computational graph. We will not be able to pass the gradient through that random sampling. So, we need to bring out the random sampling part out of the computational graph, and to do that we need to do this reparameterization trick. Yeah, so that is the correct answer. So, if we do not do the reparameterization trick, the sampling operation that we need to do on the latent space, that will become non-differentiable and we won't be able to back propagate through that operation. So, what we basically do is we just take out the sampling function out of the computational graph. So, we basically sample from a normal distribution with 0 mean identity covariance. We sample a epsilon from that, and from the encoder we try to predict the mu and sigma. We try to predict the mu and sigma of the distribution, and we just reparameterizing using z equal to mu plus sigma into epsilon. So, in that way the random sampling part, which is basically this epsilon, that goes out of the computational graph. Okay. Now, the next one, which is basically the extension of that reparameterization question. So, here the question is, which of the computational graphs correctly depict the reparameterization trick? So, here circular nodes represent random nodes and quadrilateral nodes represent deterministic nodes. So, we have to say which of these graphical computational graphs actually represent the reparameterization trick. Senthil is saying option A. Okay. Anyone else? Okay. If no other answer, then I guess everyone is agreeing, and that is of course the correct answer. So, as I already said, we have to sample from a normal distribution with 0 mean unit identity covariance epsilon number. So, since we are sampling this from a distribution, so this quantity is a random quantity. So, we have represented this as a circle, because here in the question it was said that circular nodes represent random nodes. So, this is the randomness involved in this reparameterization trick, and this mu sigma are basically predicted using the encoder. So, these are deterministic ones, like given some data point, this will be a fixed mu and sigma, and using this we predict z as z equal to mu plus sigma into epsilon, right. So, given mu, sigma and epsilon, z is also deterministic. So, only the random thing involved is this epsilon. So, so that only is the circular node, except all are quadrilateral. And also another thing is all the arrows should be towards z, like we are computing z based on this mu, sigma and epsilon. So, all the arrows should be towards z, not like this one. This is the opposite direction, this should not be the case. So, option A will be the correct answer for the reparameterization trick. Correct. Moving on to the next one. For training VAE, we want to predict an unknown distribution of latent code given an observed sample. That is, we want to predict P z given x, but that is intractable, that we have seen. So, we want to approximate it with some other distribution q z given x, which we can control by varying some known parameters. Then which of the following loss functions is used as a loss to minimize to do this thing? That we have so we want to compute this z p z given x, which is the distribution of the latent code given the observed sample, but we cannot. So, we just want to approximate it using a distribution q z given x, which we can control by varying some parameters. And to do this approximation, what should be the loss function that we should minimize? Loss function that has to be minimized. So, 4 options are there. So, which one will be the correct option among this? Senthil is saying option C. Okay. Any other answer from anyone? Sonal is saying option B, Jyoti is saying option A. So, we have got all the options as the answer. So, basically let's derive the expression to see which one is the correct option. So, what we need to do is we want to approximate P z given x by a distribution q z given x. So, to do that, what we do is we minimize the KL divergence between these two distributions. So, basically given the data, we try to adjust q so that it becomes close to the distribution P. So, we basically try to minimize the KL divergence between q z given x and pz given x. Right. This is what we want to minimize. Now, if you write down the expression of the scale divergence, this will be summation over qz given x log of pz given x. Just check it. So, yeah. Z given x by p z given x, and here the variable that we are the distribution is of the variable z. So, we will sum it over z. So, this is the expression for the KL divergence, right. Now, this one we have to minimize, right. This we have to minimize, or in other words, if you write, you can write it as summation over z q z given x log of p z given x by q z given x, right. I just swapped the numerator and denominator within the log, and that is why I brought out a minus sign in the front. So, this now this p z given x we can so now this one we can again write as q z given x log of, this is basically p x z by p of x, right. Just a minute, guys. Yeah, so this options, this is supposed to be this. So, these are not the v sign, this is basically given z given x in all of this. Yeah. So, this expression we can further simplify, and that will become right? You can simplify this. Simply I am keeping these two terms together and this px I am taking out, so that becomes log of 1 by px. So, minus log of px, and so that minus brings this sign plus. Now, here log of px is independent of z. So, we can take log of px out of the summation. So, then the summation remains only on q z given x. So, q z given x is a probability distribution over z, and if you sum over all z's, this will amount to 1. So, if you just take this part, this will amount to 1. So, this second term goes to log of px. So, our KL divergence QP has now become minus summation over z q z given x log of px z q z given x plus log of px. Or by changing the side, we can write log of px equal to KL divergence of QP plus summation over z q z given x log of px z q z given x, right. So, here your x is basically the observed data. So, that probability is constant. So, this left hand side log of px is constant. So, the sum of these two quantities, this KL divergence and this summation quantity, is constant. And initially we started from the point that we want to minimize this KL divergence. So, the sum is constant, we want to minimize this quantity. So, in order we want to maximize this quantity. So, this is basically the variational lower bound that we try to maximize. So, if we try to maximize this quantity, that means if we try to put it in terms of minimization, it will be same as minimizing the negative of this quantity. So, this we should minimize. That was the question in our case. What should be the loss that we should minimize? So, the loss should be this minus summation over z q z given x log of p x z by q z given x minus summation over z q z given x. So, option A is the correct option among these. So, Jyoti gave the correct answer among all the options. Yeah. So basically you can just derive it out, start from the objective that you want to minimize the KL divergence between QZ given x and PZ given x. So, you basically try to adjust the QZ given x parameter so that you can match it to the PZ given x. So, if you just start from there, expand it, and just simplifying that, we get this variational lower bound term here that we actually need to maximize. So, the negative of that term we should minimize. So, of course, option A is the correct answer for this. Okay. Moving on to the next one. I hope that one was clear to everyone. If anyone has any doubts, you can just stop me and ask. So, I will move on to the next one. Here we have a figure which shows the latent vector subtraction of two concepts, face with glasses and glasses. So, what will be the resultant vector? Everyone is saying option 2, which is face without glasses, which is absolutely correct. So, basically the latent vectors of VAE follows the arithmetic operations. So, the concepts actually follow arithmetics. So, if we have a concept like face without glasses and we have another concept like glasses, we can just sum it up to get face with glasses. Similarly, if we have face with glasses and we subtract the concept of glass from that, so we get face without glasses. This is as simple as that. Okay. So, these were some questions from VAE. Next, we will move on to GAN. So, the first question that we have from GAN is, when the GAN game has converged to its Nash equilibrium, that is when the discriminator randomly makes an error in distinguishing fake samples from real samples, then what is the probability of belongingness to real class given by the discriminator to a fake generated sample? Probability of belonging to the real class for a fake generated sample. What should be that probability? Can anyone guess what will be the answer for this? So, basically when your GAN has completely learned, so it is at the Nash equilibrium position, then you give a fake sample to your generator, and your generator output is basically the probability of the input sample belonging to real class. So, what will be that output probability when you give a fake sample to the discriminator? So, we can of course derive this through expressions, but intuitively what you guys think will be the probability? Senthil Kumar is saying option 2, which is 0.5. Okay. Anyone else? Jyoti is also saying option 2. Yeah, correct. Option 2 is the correct option, which is 0.5 probability. Sonal is saying 0.25. Okay, that's not the correct answer. Correct answer is 0.5. So, the intuition behind this is, now your GAN has reached its equilibrium position. So, that means your generator has completely learned how to generate the data that you want. So, it can very well fake the samples. So, its generated fake samples will look really like a real sample, right. Now, your discriminator, it has also learned how to discriminate real and fake, but now since it is at equilibrium, so your generator sample has become so good now that your discriminator can't discriminate. That is why you have reached your Nash equilibrium and your GAN training has converged, because your your generator is able to produce such samples which your discriminator cannot realize that this is a fake sample or it is a real sample. It cannot distinguish between the two, everything looks same to it. So, if that is the case, it has two classes to classify, one is fake, one is real. So, if given any sample, be it a real sample or be it a fake sample, and it has no clue of how to distinguish it, the discriminator does not know any way of distinguishing it, it's completely at the confusion state. So, what it can do is it can do a random coin toss. So, it can just do a coin toss. So, that way you have two probable options. So, probability of putting in each will be half. So, belonging to the real class for a fake sample is half. So, that is the intuition behind it. So, your discriminator is completely confused. So, it randomly assigns to one of the classes. So, 50% time it will assign to real class, 50% time to this class. So, it is like 0.5 probability of belonging to the real class. But that is the intuition wise the answer, but we can also derive this mathematically to see this is actually the case. So, for that we will start with the objective function for discriminator training. So, when we want to train the discriminator, what we want, that it should, for the real samples, it should give probability close to 1. So, output is, let us say the discriminator given a sample x, the discriminator output is dx, which is basically the probability of belonging to the real class, right. So, what we want for discriminator training, that given a real sample x, the discriminator should give very high value, almost 1 for dx, whereas given a fixed sample, this dx should be very low, close to 0. That is what we want for from the discriminator. So, based on that, what was our objective function for training the discriminator? We had to maximize over D the expectation of x belonging to the original data distribution log of dx plus expectation of log of 1 minus d of g of z, right. So, this was our objective function to maximize. So, when the data comes from the original distribution, which is the P data, this distribution, if x belong to that distribution, then you should maximize the value of dx, or you should maximize the value of log of d of x, or in one term you can write it as that whatever be the value of x, if it belongs to the real data distribution, the expectation over all these types of x which belongs to the real data distribution, expectation over all those for the value of log of d of x should be maximized. Whereas, if we have a fake sample, that is we have started from the noise distribution, which is basically the z and which follows this distribution PZZ. If we have sampled the noise from that and passed it through the generator and obtained this GZ as the fake sample and put it through the discriminator, then it should give very low probability of belonging to the real class. That is, it should give so this d of g of z, it should be very low value. That is 1 minus d of g of z should be a high value. So, log of that thing, expectation of that with respect to z, that has to be maximized. So, this is basically our objective, we have to maximize this quantity. Now, given a latent z sampled from this PZ distribution, which is the noise input kind of thing, the mapping G, which is basically the generator, that is a deterministic thing. Once you have freezed the weights at some iteration, let us say, that is a deterministic mapping. So, given one particular z, you will get one particular GZ, and this GZ is basically your fake sample. You can write it, this is like equivalent to x. So, this is your fake sample, this G of z is basically your fake sample x, and this mapping is deterministic. So, given z belonging to this distribution PZZ is equivalent to having x belonging to the distribution PGX, which is basically the distribution of the generated samples from the generator. So, this is basically the distribution that the generator models. So, it maps each z belonging to this PZ distribution to a x which belongs to this PG distribution. So, since this mapping is equivalent, we can write this expectation as x belonging to PGX log of 1 minus d of x. So, having this quantity log of 1 minus d of g of z and its expectation with respect to PZ is equivalent to having here d of x and taking the distribution of x as the PGX, right. So, we can write this expectation term like this, and if we keep the first term as it is, now, if we expand it in the form of integration, if we write down the formula for this expectation, so the first term will be integration of p data x log of dx over all x, and the second one will be integration over all x p gx log of 1 minus dx dx. So we can club it together. So it's of the form integration over x p data x log of dx plus pgx log of 1 minus dx entire into dx. So this is what we have to maximize. Now if we want to maximize this quantity, that means for each x, this is equivalent to for each x, if we maximize this term, then we will be done. We will be able to maximize the entire term with respect to d. So for each x, we have to maximize this particular term. So this is basically of the form a log of y plus b log of 1 minus y. You see here this p data x basically is a and pgx is basically b. So here we are assuming that we have fixed the generator for now and we are trying to optimize the discriminator, right. So this pgx is for now constant. So these a and b are constant and here we have log of y if we take dx as y and here we have log of 1 minus y. So this is basically the function, let us write it as f, that we need to maximize with respect to y for each x value. So if you just try to maximize it, what we should do is we should take the first derivative and equal it to 0. So if you just take the first derivative for this, that will become a by y minus b by 1 minus y, right. And to maximize the expression f, we should make this 0. So this is basically df dy with respect to y we are trying to maximize. So that means a by y is equal to b by 1 minus y, or we can write 1 minus y by y is b by a. That means 1 by y is a plus b by a. So y has to be a by a plus b. So this expression will be maximized when y is equal to a by a plus b. So in our case that means the expression was p data x log of dx plus pgx log of 1 minus dx. This is what we have to maximize to train our this has to be maximized for all x to train our discriminator. So if we put the same formula that we obtained here like this should be a by a plus b. So our optimum d, which is if we write d star of x, that should be equal to p data x by p data x plus pg x for all x. So this is basically given one pg x, this is the optimal discriminator that can be learned. So now when you are at the Nash equilibrium, that means your generator has also learned to mimic the data distribution. So at Nash equilibrium you have your p data x and pg x equal. So your pg x has become equal to your p data x at the Nash equilibrium. So in that case your d star x will become half for all x. So given a fake sample or a real sample, the probability that the discriminator will give as output, which is the probability of belonging to the real class, that should be half. Okay. That is how you can derive this also, and intuitively also you can think that the discriminator is completely confused now between the two groups, like which one is fake, which one is real. So it will randomly assign. So probability of randomly assign between two classes is half. Okay. I hope the derivation is clear to everyone. Now let us move on to the next question. So the next question is, which of the following losses can be used to optimize for generator's objective by minimizing with gradient descent optimizer? Okay. So for generator, what should be the generator's objective function? That you will minimize with gradient descent. Among these, what can be used as the generator's objective? And here formula for cross entropy has been given, and here by dg of z we mean the probability of belonging to real class as input by the discriminator for a given generated sample gz. So given a generated sample gz, d of g of z is probability of belonging to real class as output by the discriminator. So given that, what should be the generator's objective that you have to minimize? So basically, to learn the generator, what we do, so what we want for training the generator, that the generator should produce such fake samples that the discriminator cannot distinguish. So that the discriminator will think this fake sample as the real samples. So the generator should be such that the sample that it outputs, that the g of z, if that is given to the discriminator, it will classify it as a real class. So d of g of z should be close to 1, right. So if you now try to see the options, the first option is the cross entropy between 1 and d of g of z. If we put this in the cross entropy expression given here, what it becomes? It simply becomes minus a is 1 log of d of g of z, then 1 minus a, since a is 1, the second term goes to 0. So your cross entropy becomes this. So now what is our objective? We said we want to maximize d of g of z. We want to make it close to 1, that probability. So we want to maximize this. So we want to maximize the log of d of g of z. So here we have a negative sign, so we have to minimize this quantity. So this is a objective function that can be minimized for generator training. If we see the next one, so the next one, if you put in the same expression, it becomes minus a is again 1, so the second term will go to 0. You have right, you have this, your b is minus d of g of z. So if you want to maximize d of g of z, you should minimize minus of d of g of z. So minimize the log of that, so the negative of that you should maximize. So this should not be minimized for your generator training, right. Similarly, if you see this one, so here what you are trying to do, you are trying to here this is the cross entropy between 1 and 1 minus d of g of z. So if you think in terms of cross entropy, that you are trying to match 1 to 1 minus d of g of z. So here also your expression will become log of 1 minus d of g of z. So again you have to maximize this. So you have to maximize this. So you should minimize this thing. So you should minimize the log of that and maximize the negative of that. So this can't be used, this can't be used, because you want to minimize. And the last one, that becomes log of 1 by d of g of z. So that will become log of d of g of z. So if you want to maximize this, you have to maximize this. So you can't minimize. So option A is the only option that you can minimize to train your generator. Okay. Now similarly, the next question is, which of the following losses cannot be used to optimize for discriminator objective by maximizing with gradient ascent. So, here your objective function you want such that you have to maximize that objective function to learn your discriminator. So, can anyone guess which will be the correct option here? Which of these losses you cannot use to train your discriminator? So, the idea is in case of when you are trying to, so here one more thing, I did not read this part. So, while these losses cannot be used to optimize for discriminator objective while only sampling from distribution of generated samples. So, you are just training the discriminator with samples sampled from the distribution of generated samples. So, you are just training your discriminator with the fixed samples, and you want to use a loss function which you want to maximize, then which of this cannot be used? So, if you are using only the fixed samples, so what you want for the discriminator to decide that these are fixed samples. So, the probability of belonging to real class should be as low as possible. So, you want to minimize the d of g of z. So, given that, can anyone tell me which one will be the option or which loss you cannot use for this? Jyoti is saying option 2. Okay. So, let us see what will happen if we have option 2. So, basically if I expand this becomes minus minus will become plus, a is 1, so only the plus term, log of d of g of z. So, what we said that we want to minimize d of g of z because we just have fixed samples and we want the discriminator to perform well. So, it should classify these as fixed samples. So, d of g of z should be minimized. So, the log of that should also be minimized. So, we cannot use this function for maximization. So, of course, this is the correct answer, that this cannot be used for maximizing. So, if you see the first option will basically lead to minus of this, right, minus of log of d of g of z. So, basically if you want to minimize log of d of if you want to minimize d of g of z, you have to maximize this quantity. So, this can be used. Similarly, for the third option, this will become log of 1 plus d of g of z. So, you want to minimize this. So, this you want to minimize, this you want to minimize. When you have the minus sign, you have to maximize this. So, that is also possible. And the last one here, you have log of 1 minus d of g of z. So, if you want to minimize this, you have to maximize this entire thing. So, you have to maximize the log of that also. So, that also can be used as an objective function which has to be maximized. Only option 2 cannot be used because that one, if you want to use, you have to minimize that. Okay. So, I hope all these were clear to everyone. So, these were some of the problems that I planned. Now, let us discuss a few problems from this week's assignment, the week 12 assignment. Some of those problems we will discuss and we will end with that. So, this was one problem that you had in the assignment, that there are two distributions. The first distribution P is a uniform distribution between -1 to 1 and Q is a normal distribution. Then what will be the Kehl divergence QP? So, what is the answer for this? I think option 4, infinity. Yeah. Option 4, infinity is the correct answer. So, how do you compute that? So KL of Q given P you have to compute. So since these are continuous distributions, your expression of this will become this, right? Now your Qx is a normal distribution, so it is defined for all values of x, but your Px is a uniform distribution between -1 to 1. So for all other values outside -1 to 1, the value of P of x is 0. So this quantity will become 0 at many x values. If this becomes 0, this fraction, this entire fraction goes to infinity. So log will go to infinity. This entire expression now goes to infinity. So your KL divergence tends to infinity. So it's completely different. Okay, the next one. Which of the following is true regarding the reconstruction loss realized as mean squared error between input and predicted signal of standard autoencoder? First option is such loss is not differentiable and cannot be used for backpropagation. Such loss tends to form distinct clusters in latent space. Such loss cannot be optimized with gradient of descent, and none of the above. Anyone? Sonal is saying option B, which is such loss tends to form distinct clusters in latent space. Of course, that is the correct answer. So when we have an autoencoder and we just try to minimize the reconstruction loss, we basically learn latent representations which are compact as well as sparse. So for different types of data points, for example, for the MNIST different types of numbers like 0, 1, we will get different clusters. This actually helps the decoder of the autoencoder to correctly decode the data, the original data from the encoded latent vector. So to maintain that distinct structure of the data or the class belongingness of the data, this loss function will try to form distinct clusters for the different types of data in the latent space. And of course, it is differentiable, it can be backpropagated and it can be optimized, because that is how autoencoder is optimized. Next one. For an autoencoder, suppose we give an input signal x and reconstruct a signal y. Which of the following objective functions can be minimized to train the parameters of the autoencoder using gradient descent? So, which of these you have to minimize if you want to train the autoencoder? Any answer? Everyone is saying option 3, which is of course the correct option. So basically, if we see this, if we just plot x minus y, so x minus y is basically our error between the input signal and the reconstructed signal. So this error has to be minimized. So your loss should be such that when this error is low, your loss value should also be low. So loss value should be low in this region and increased towards this region as the difference increases. Now if you put the first one, exponential of minus of mod of x minus y, that will be something like this. So as your x and y difference increases, your loss value decreases. So that can't be on optimization. So that can't be a objective function. If we see the next one, minus log of this will also be something like this. This will also like for low value where your x and y are matching, there you have a higher loss value. Now the third one, the exponential, that curve is basically this, right. So as your difference between x and y increases towards this direction, your loss also increases, and when you have very less difference between x and y, which is around this region, then you have low value of loss. So that is a possible loss function. And x plus y whole square, that is of course that's not even related to the error. So that's not a possible option. So this is the correct option. This loss can be used. Next one. Suppose we have a 2n dimensional normal distribution in which we assume all components are independent of each other. Then what will be the size or number of elements of the vector to fully represent the covariance matrix of this distribution? So what do you think will be the size or the number of elements that you need to fully represent the covariance matrix of the distribution? Money is saying option 2, 2n, yeah, correct. So when you have independent, all components are independent, that means your covariance matrix will be diagonal. All the off diagonal elements, which basically denotes the cross correlation between different components, those will be zeros. So only elements you have are the elements on the diagonals. So since you have a 2n dimensional normal distribution, you will have the covariance matrix will basically be 2n cross 2n. So you will have 2n number of diagonal elements. So that many is sufficient to represent the covariance matrix, and this is how what is done in VAE also. In VAE you try to predict only this diagonal elements of the covariance matrix, not the entire covariance matrix. Okay. Moving on to the next one. What will happen if we do not enforce scale divergence loss in VAE latent code space? The latent code distribution will mimic zero mean and unit variance normal distribution. Network will learn to form distinctive clusters with high standard deviation for each cluster. Network will learn to form distinctive clusters with low standard deviation of each cluster, and none of the above. So what will happen if you do not enforce scale divergence loss? Sonal is saying option C, which is the correct option. Yeah. The network will learn to form distinctive clusters with low standard deviation for each cluster. So basically, if you do not have scale divergence loss, the only loss that you have is the reconstruction loss, which basically reduces to an autoencoder. In that case, you have distinct clusters in your latent space, and also the training will try to reduce the standard deviation of those clusters, so that the decoder do not encounter any confusion between different clusters. So given a data point, it can clearly know that which type of data this latent code belongs to. So the standard deviations are also really less of these clusters. Now when you impose the scale divergence loss, you try to push all the distribution towards zero mean unit covariance. So overall your entire latent code space becomes compact, though there is small clusters within the data which comes because of this reconstruction loss, but overall it becomes much more compact, so that you can interpolate within the data points. Okay. The next one, which of the following statements is true in the original GAN training? It is desired that the discriminator loss monotonically goes down, generator loss monotonically goes down, discriminator loss goes down while generator loss goes up. It is desired that neither of the losses of discriminator or generator monotonically goes down or up. Anyone? Option D. Okay. Yeah, that's the correct option. So when you train GAN, that is basically a zero sum non cooperation kind of a game. So your discriminator tries to fail your generator tries to fail your discriminator, but if one of their loss monotonically goes down, or let's say one of them wins, then the other one actually fails, then you do not reach the equilibrium. So if you or if one of their loss goes monotonically up, that means that one fails, so other one wins. So that cannot happen. So none of them can go monotonically up or down for the equilibrium to be reached. Now the last one. Suppose we have trained a VAE on phases with 4D latent code, and after convergence the mean vector and standard deviation vector are given by these two. This is the mean vector, this is the standard deviation vector. Now in the evaluation phase we pass a new phase image belonging to the same domain. Which of the following latent code is most probable to be encountered when we pass this new phase image? So which one do you think will be the most probable latent vector representation for the new phase? 4 options, which one do you think, guys? Closest is 2, option 2. Yeah, of course, option 2 is the correct answer. So what has happened? The VAE has learnt the latent space for which the mean vector is at 2.1, minus 1.9, 3.8 and 0.9. So it has learnt to map your phases to a distribution with this mean. So if you give a similar type of phase image, it will try to map as close possible to the mean vector, because that's where it is mostly concentrated. So it will be close to the mean vectors. So among the 4 options that are given, if you compute the Euclidean distance of these with the mean vector that the encoder has learnt, so you will see the option 2 has the lowest Euclidean distance. So basically that is 0.1. So this has the lowest Euclidean distance. So this is closest to the mean vector. So this is the most probable one to be generated as a latent vector representation of the new phase. Okay. So these were the problems planned for today, the last session of problem solving for this course. So if any of you have any doubts, we can discuss that now. question: do we have any reference to learn VAE or GAN apart from the class course? There is no such course reference available, but you can of course go through the original VAE or GAN paper. That will have all the details of it, but it will be in very much detail. All derivations, everything will be there. If you just search for the VAE paper or GAN Goodfellow paper, you will get those papers online. You can just go through those. Problem 15. Okay, so this one you were saying. So basically when you are training a GAN, basically what happens is your generator tries to learn how to generate fake samples that looks like real samples, right? It tries to deceive the discriminator so that it cannot differentiate between real and fake samples, whereas the discriminator basically tries to give the generator a hard time by discriminating every time between the real and fake samples. So this is a kind of zero sum game goes on. So this one tries to fail that one tries to fail this one, and when both of these reaches the equilibrium, that's the best possible option. So to have your training, so if one of them fails, let's say your discriminator is failing, then your generator is not getting a good feedback. So your generator is learning based on your discriminator performance, right? So if the discriminator is very good in differentiating the two classes, still it cannot differentiate, it's confused, then your generator can have that good feedback. But if the discriminator itself is failing to do the classification, then your generator will not have that good feedback. On the other hand, if your generator itself is failing, that's also not a good thing. So two of them each is trying to fail the other one, but if one of them actually fails, then the other one completely wins. If that is the situation, then that equilibrium can't be reached and your optimal training can't happen. So none of their loss is monotonically going down, means they are actually they are actually winning the game. So if one of them wins, the other one will lose. So that we cannot afford to have. So none of them can lose, none of them can lose. So that's why none of their losses can go down or the other ones go up. So that cannot happen. It will be at an equilibrium position. I hope that makes sense. Okay, so if there is no more question from anyone, so does it mean the GAN is used for chess? So does it mean that GAN is used for chess chess in the sense like the chess games, online chess games that you have? I don't think it's like this game theoretic concepts will be used in there. It won't be GAN exactly, but these zero sum game kind of concepts will of course be used there. GAN is basically a generative model. So, once you have trained your GAN, then your discriminator is of no use. Once your training is done, you just discard the discriminator, you just use your generator and you keep on generating new samples like the one you want to generate. So, that is the only use for GAN, but in chess games, yeah, this kind of theory is of course used. Thanks for your sessions. Thank you, Sanjay Kumar. If that helps, then that's nice to hear too. Okay, so if there is no more question from anyone, then we'll close this session today. So I hope and thank you first of all everyone for joining through this entire 12 weeks, and best of luck for your exams, and I hope somehow my sessions were helpful and you enjoyed solving these problems. I hope I could explain a bit of it to you. So yeah, thank you everyone for joining through this sessions with me. Bye, best of luck.